What's up, guys? Welcome to another one of our videos on Back to Basics. What we're going to be looking at today is, as the title suggests, we're going to be looking at the D Latch. Basically, what this is a memory device, very simple one, that's used in what they call 7400 logic. Basically, it is a device that you can latch up or store the previous value. No matter what the input does, it'll always output the previous value until you tell it to change. Now, how this is accomplished, I'm just going to go through a very simple rundown of it. You can look up D latches or D flip-flops, or there's JK flip-flops and SR latches and all that fun stuff. There's a bazillion different types. But what we're going to look at is just a simple D latch for now. Like I said, it's just going to be a basics video, so nothing real in depth. We're just going to go over basic functionality of it, and this is kind of a prequel into the next set of hardware specific videos that we're going to be doing, which will involve multiple D latches to create some pretty cool effects with some LEDs. So without further ado, we're going to look at the D latch, the common symbol for a D latch. Well, if I can draw properly here. Oh my heavens, didn't mean to do that. Okay. So if I can draw this, all right, a simple D latch, usually there's a D input, okay? There's usually some sort of clock. May have to make this bigger. And then there's usually, a lot of times, here we'll make this like this so we can make it a little bit bigger. There we go. Usually there is some sort of a reset. Okay, some sort of a reset here. And then there is usually two outputs. They're labeled as Q and Q bar. Okay. Now, what does all this mean? Okay. Well, I'm going to tell you. Here we go. Okay, the D is going to be our input. So this is the input. Okay. This clock is our clocking signal, which means we're going to give it a signal basically like a PWM wave, okay? Some sort of clocking signal, all right? Then the reset, what this guy is he's an inverted output. That's what a circle means. If you ever see a data sheet for digital logic, like any types of latches or flip-flops or any type of 7400 logic, like an AND gate, NOR gates, OR gates, XOR gates, all that fun stuff. If you see a little circle, usually that denotes a knotted, which means it's inverted. Basically, a 0 will make it active, and a 1 will, or a 0 will activate whatever function that is, and a 1 will inhibit it. So essentially on this one, to reset this guy, you have to feed it a 0. Otherwise, you have to hold it at a 1. Okay, is how that works. So what we do here, and then we've got Q is our output. Okay, now the Q bar, what Q bar means, those of you that don't know much about the digital logic notation, a bar above something means not. It's like the same thing as this little circle right here. It's like the same thing as doing that. So it's saying that this is the knotted version. This output here is basically the knotted version of the output up above, so the knotted bar. So if this guy up here was a 1, then this guy down here is going to be a 0. It's going to be the inverse of it, the knotted. Similarly, if you got this guy up top here, this guy is a 0, then this guy down here will be a 1. Okay, so pretty simple, straightforward, right? Okay. So that's essentially the different parts of our D flip-flop. Now let's go ahead and we will look at a truth table of the D flip-flop. So for a truth table, okay, of our D flip-flop, truth tables are always like a type of table. Oops, got something smeared on my screen, so I'm trying to wipe it off, and it's drawing lines. Okay, on the truth table that we got going on, you're going to have your D input. You're going to have your clock. Okay, and then you're going to have your output. And we're going to say that we never reset this chip, just for all intents and purposes. So I guess we can say the R set. We're going to say, remember, it's inverted. So the R set for everything. Okay, our inputs can either be a 0 or a 1. So our R is always 1 because we don't want it to ever reset. Remember, it was inverted, so if you give it a 0, it'll reset, which basically means it'll clear the output. It'll return whatever. If the output's a 0 or a 1, it'll always return it to a 0 when you reset. Always 0 is the output. Just keep that in mind. If you ever reset D flip-flop, it'll always go to 0. Of course, I shouldn't say always. There might be some that have it inverted, but I'm not, 100% on that. So anyway, so depending on what our clock does, okay, so it will be at it depends on the edge, okay? So there's what's called an edge triggering. There's either positive edge, like this, which this is plus edge. Let's hope I can write this in. Yeah, there's positive edge. And then there's negative edge, which is on the falling edge. Okay, those are our two different types of edges, okay, that we can have with these. So what positive edge means is when the clock right here, this piece, when the clock goes from 0 to 1, basically on the upstroke of the PWM wave, it will take whatever's at the input, whatever at the D, okay, whatever at the input, and it will put it at the output. Okay? Is what that means. Only when the clock is going up. Okay? So, essentially what we got going on here is we got this clock here. So let's say the clock goes up here, then the output's going to be 0. Okay? Now, if for some reason, let's say we're going with time here. Let's say the clock output is going down. This is for a positively edged, I should say that. Positively edged triggered. So if we're doing this one, it'll clock the 0 over. Now, if this is the falling edge, it doesn't do anything. It doesn't move anything. It doesn't clock anything in, so it's still going to be a 0. Okay? Now, if we give it another 1, but it's on the upstroke of the clock, the edge is going up, so it's like the next edge after the first one. When it comes up, now it's going to pull the 1 in. Okay, and our reset bit is still 1. Okay, so there we go. So as the clock is going, it's just keeping that 1 in there. Okay, so hopefully that makes sense. So essentially, that's how these guys function. Is whenever the clock is moving on the upstroke, if it's a positively edge triggered device, it will clock in whatever's at the input, it will put on the output. Okay, so now and then similarly, if this was the other way around, if we were doing a negatively triggered one, this would still be 0, this would be the 1, and then this would remain 1 because it wouldn't do anything. Okay, so that's if it was negatively triggered, if we were choosing this one. So anyway, so that's basically the truth table of it. That's how it basically works. It's very simple. Okay guys, so what we're going to do is we're going to draw ourselves basically a 4-bit shift register with using these D flip-flops or D latches, whatever you want to call them. So I'm going to draw 4 of these guys. 2, 3, and then let's draw the 4th one. Okay, so we've got our D, we got a Q, we got a D. Whoops, that looks more like a B. Let's get rid of that. Let's go. It's going to be a D and a Q and a D, Q, D, Q. For simplicity, I'm just going to show the clock as this little wedge here. Okay, and then I'm not going to show the reset pin or the Q bar just because we're not going to use them, so I'm not going to show them. It makes the drawing a little simpler to look at. Basically what we're going to look at is we're going to make a shift register, which basically is like a Christmas light string. You know how Christmas lights will start at one end of the string and turn the light on, and then the light moves to the next LED or lamp that's in the row, and then the next, and the next, and the next, and the next, and the next, so on and so forth. Well, you can do that using these little guys. So what you do is you're going to take the output, and you're also going to feed it back to the input of the next stage. Take the output out, but then also feed it back to the next stage. Okay, same thing here. There's an output here. You're going to feed it back to the next stage. So what happens is you take all the clocking signals, bring them all out, but you're going to tie all of the clocks together. Oops, a little longer than I wanted it. Okay, you're going to tie all these clocks together. And then you're going to produce basically a waveform that's here. Whoops, I didn't mean to change pages. Let's go back. Okay, so you're going to produce 1, 2, 3, 4 clock pulses. Okay, so you got 4 clock pulses that you're going to work with. What we're going to do is we're going to take the number of the binary number 1. Okay, so we're going to go 0, 0, 0, 1 is what we're going to shift into this guy. And how this is going to work is on the first clock pulse. Okay, the first bit is going to appear, or is going to be set at the same time. It's going to be set on the input of our D latch. When that is there and the first clock pulse is issued, this first clock pulse, it is going to latch that 1 in the output. So we're going to get a 1 here. Or basically, if you had LEDs on this, you're going to get an LED turn on. Okay. At the same time, it's going to put the 1 also here because we're feeding it to the next stage. Now at the second clock pulse, we're going to push this 0 to the input, which at that clock pulse, it'll shift that 0 in, and that 0 will come to the output. Now, at the same time, simultaneously, at our second stage, since we had a 1 sitting there when we issued the clock pulse, it's going to shift that 1 out before it becomes a 0. Okay? So the light just moved from this output to this output now. Similarly, on the third clock pulse that comes in, we're going to be pushing the third 0 over to here. So this one will remain 0. Okay. However, the one that came here because of the previous one will get shifted out to here. And the 0 that's on the second stage will get shifted out as well. So then now this becomes 0. And so our 1 just moved to here. And then lastly, at the last clock pulse, our final 0 is going to go in there at the top, which then, okay, this is a 1 too because of this guy being a 1. Okay. So it will basically do the same thing here. It will shift the 1 out here and then shift the 0 here, which then will make this 0. And there we go. So we have just progressively moved our 1 down through there, and if you look, we have 0, 0, 0, 1, just like our number that we started with. Okay? So that's how the shift registers work. Now, one thing that is different, though, about like a 595 chip, which you've seen me use in the past, and if you don't, you can check out those videos that are basically doing serial to parallel, basically taking a serial signal, which is exactly what we just did, and converting it to a parallel set of outputs. Now, they are a little bit different. They have what's called an output latch, which basically is another set of these latches, but without the second part connecting in. And in fact, here I can just show you it. It'll just take me a second to draw it. If we take all, let me take all this off. Let's get rid of all this. Woo! So essentially, see if I can get rid of this without blowing away my drawings. Ooh, iPads. iPads are definitely interesting beasts. Okay, so let's get rid of this. Okay. The problem that this configuration ensues is if you're not trying to make Christmas lights, you're just wanting to serialize some data, what will happen is your data will be sitting there changing. Be changing all the time as you're shifting your data in, right? Because as you saw, the light turns on and moves down the output row. Well, you don't want that when you're, maybe wanting to turn on specific LEDs. So what you need to do is allow this section here to wiggle around, as you're loading in your zeros and ones, until you get the 0, 1, 0, 1, until you get that in there, because it's going to be shifting around once it gets in there. To avoid that happening at your output, what you do is you will put an output latch on. And let me show you. Let me shorten this up so I can draw it. It will be another series of these guys. Let me see if I can. I'll just draw it. It'll be another series of these guys. Okay. You'll have your D and your Q. That almost looks like a P, but you know what I'm talking about. D and a Q and a D and a Q and a D and a Q, and then you got your clock. Put our clock in there. Okay. They just bring these straight away. Whoops. It's actually fairly simple. They just bring these straight away. Oh, good grief. My pen is not functioning. Oh, well. They bring them straight in to the inputs. They use these basically as a buffer. And then what they'll have is another input. Okay. And let's see if I can do this. Jump over this. Go there. Jump over that one. Go there. Trying to make little dots is interesting. Jump over that one and go there. Okay. So now we have our outputs. Okay. So it almost looks like the same thing that we had before, just a little different. And what this one will do is as you are putting your clock pulses, you've got your clock pulses coming in, you got your 0, oh crud. You got your like 0, 1, 0, 1 or something. Whoops, draw the 1. Going in there. These outputs here in this section will move around as your clocking signal goes in. However, obviously, just the nature of the D flip-flop, nothing is going to appear on the outputs out here until, and let's say this is all positive edge, okay? Let's say this is all positive edge. Until this clock line down here gets a bump in it. Basically, you get that positive edge right there. Then all of these inputs here and here and there will now shift that, and let's say that that's what we have. We have the 0, 1, 0, 1. Once you receive this gating signal right here, it will then and only then will it actually shift it to where it comes out, and it comes out all at once simultaneously. That's basically how they're doing that, and that's why you'll have 3 different lines. You'll have your serial data line, you'll have your serial clock line, and then you'll have your latch clock, or they'll call it an R for register clock or something like that, or they'll call it an LCLK or something like that for latch clock. But that's what that is. That's so that you can roll your data in up here and not affect your output, that's out here. You don't affect your output until you want to, until you give the clocking signal to these output registers to actually move it out. So anyway, that's basically in a nutshell. I hope this wasn't too complicated for everyone to understand, but if you have any questions, you can always put it in the comments and let me know. But this is basically how D flip-flops are used, and just, I guess, latches in general are used for for doing multiple I/O, like expanding your I/O. This way you can take 3 pins, and like I said, you just keep cascading these together. You know how we did this method of taking the output and putting it on the input and just keep going? Now there's a limit, obviously, because you've got I squared R losses and so on and so forth. So there is a limit of how many you could stack together. But in theory, you could stack up. You could have 3 pins, basically your serial data, your serial clock, and your R clock here, and have, like, let's say 32 outputs. You could have 32 of these latches put together. So you could and have a 32-bit number that you're using. So like I used a 4-bit up here. You could be using a 32-bit number is what you'd be using. And then you'd be controlling individually 32 different LEDs, but only using 3 wires, 3 physical wires or 3 ports on your microcontroller. So pretty cool. So what I'm going to do is I'm going to show you guys how to do this in the next set of videos, how to implement something similar to this and run it, basically make your own Christmas lights type of a deal. So it ought to be pretty cool, but it'll be all hardware. There'll be no programs to it. So stay tuned, guys. Like, subscribe, share. I do enjoy the support and all of the comments that you guys give me. It's fantastic. I love the response that I get. So if you have any questions, anything didn't make any sense, please shoot me a comment or a personal message or whatever you feel like doing. Get a hold of me and ask me. And if I'm not available, I have launched a new forum that is just for us, that we all can take a part of. So if you want to be one of the first people to get in there, it's themagicsmoke.proboards.com. There'll be a link in the description. Please check that out, sign up, become a member. It'd be great to build a community there as well. So that way, if I can't get a hold, you guys can't get a hold of me or whatever for whatever reason, or you can't find this, you can always go there, and hopefully we'll all be available. Someone will see your question and be able to answer it for you. So anyway, guys, that's it. I'm out. Take care. Keep coding. Keep building. And keep having fun, because that's what electronics is all about, is how much fun can one person have, right? So anyway, guys, thanks again. Take care. And with that ought to do it.